going through the giant puddle at the bottom of the road.
Lock both ends as far as I know.
It's,
You have to hook wash the way back out.
Sorry. Right. So, yeah, it's about past, so I don't think we'll be getting many ones. I apologise for the small audience, but unfortunately the weather is against us.
I think half the roads are blocked round about the locality.
Yeah,
Yes.
everything's flooded out. So.
Oh, there's somebody else. Driving through the floods.
Got a lake come out, yeah, in you come. I think there's a cable there.
No, in front of you.
In front of us. Glad you could make it through this horrendous weather.
There was a terrible torrential downpour for a few seconds I was on the way.
Typical. Yes. Right, so anyway, tonight's speaker is Dr. Eugene Vasiliev from University of Edinburgh, for Royal Observatory Edinburgh, I should say. Eugene did his MSc and PhD in Moscow, and then moved over to Rochester in the US to do postdoc work, which he followed with a spell at Oxford University and then at Cambridge University. So certainly been to some prestigious establishments and departments there. He's now working at the Royal Observatory Edinburgh, developing software for telescopes as part of the team there. And tonight he's going to talk to us about his real passion, I think, which is
One of my real passions,
yes, which is the life and adventures of binary supermassive black holes, which I think should be amazing because we all love our black holes and gravitational waves. So I'll hand over to Eugene.
Thank you for the introduction. And yes, indeed, I'm going to talk to you about these mysterious beasts, supermassive black holes, and especially binary supermassive black holes. So I guess the audience here looks like should be aware of what black holes are. I can ask you a question, how would you interpret this picture here on the front slide?
You seem to be making the black holes out to be villains.
Yes. What else do you see in this picture?
Eat up things.
They eat up things.
And
Yeah.
kick things out.
Yeah, they kick things out. That's probably more relevant to the subject of my talk, yes. And of course, since this is kind of artist's impression, but it's in fact created by one of my colleagues, and it's based on a real story. So you will hear this story unfolding as time goes on. So, supermassive black holes, what these are. Here, these pictures, perhaps this one you might recognize. I think it's from Interstellar, or at least something related. This one is more like a typical artist's impression of a galaxy with a black hole in the center. But these are not real astronomical images, rather impressions. However, they convey the idea that the black hole is black, right? So that's the main defining feature of a black hole, that it must be black. But we see it not because it's black, but because it's surrounded by matter. And the matter around the black hole moves with very high velocities because the gravity of the black hole is strong. So gas around the black holes moves with high velocities, creates a lot of friction, emits a lot of light, and the gas also can escape through these kind of jets that are perpendicular to the orbital plane of the gas. And that's how we see the black holes in practice, right? We don't see the black holes themselves, but we see the light emitted by the gas. And we tend to think of black holes as kind of super villains in a way. They're kind of sucking up all the matter and eating the stars around them, but in fact they're not really villains at all. They're normal denizens of a galaxy, except that they're perhaps more like kings of the galaxy because they're sitting in the center, and they also govern quite a lot in the galaxy. Maybe not the entire life, but quite a lot of it. However, that's not the main subject of my talk. It's just to mention that supermassive black holes are really big things. They're similar to ordinary black holes or stellar mass black holes, but they're just a million times or billion times more massive. And the defining feature is that they stay in the centers of the galaxies. Real astronomical images look more like this. So here is an example of a galaxy, M87, the galaxy in the Cygnus constellation, one of the nearest extremely massive elliptical galaxies. And it's one of the targets of recent observations by the Event Horizon Telescope. So if you zoom on the galaxy's center, we see that in the galaxy itself, it's in a different wavelength range. I think it's the radio that you see here. You see these two kind of jets emanating from the center. And if you zoom in the very, very, very center of this whole thing, that's the image that was, I think, put up a few years ago as the first portrait of a black hole, a scientifically accurate portrait. Although some people say that it's maybe just fake news, and in fact, what they have is recording our data. But, nevertheless, this is an image of one of the black holes. Another one that was observed by the same collaboration, the Event Horizon Telescope, a couple of years later, is the black hole in the center of our own galaxy. I don't have a pretty picture of it, but it looks kind of similar, not unlike this one. But we knew quite a long time ago that there is a black hole in the center of our galaxy, and the reason why we knew that is that we see the motion of stars in the very center of our galaxy. And this picture here shows the trajectories of a dozen of stars having been observed by big 8-meter class telescopes in Hawaii and in Chile, in BLT. Tracking this motion of stars over many years, and we see that it actually orbits some central point mass. And what else could it be other than the black hole? Because the mass here is pretty large. That black hole has a mass of almost 6 billion solar masses. This one is 1,000 times smaller, but it's still a pretty chunky one, 4 million solar masses. And that's the range of masses that kind of brackets the values typical of all other galaxies in a sense. So supermassive black holes are typically between 1 million and a few billion solar masses, although there might be smaller ones, but they're much harder to detect. And by the way, this image here was, well, not the image itself, but the research that stands behind it was recently awarded a Nobel Prize in 2020, I think. Yes, that was 2020, for the great groundbreaking observations that led to the confirmation, as the Nobel Committee says it, frames it, a dark massive object. They don't say that it's a black hole, but almost everyone is pretty sure that there could be nothing else if we believe that we know everything about the universe, which of course is perhaps not true. So, for all intents and purposes, what sits in the center of our galaxy must be a black hole or something that looks very similar to a black hole. Anyway, so this is this is a single black hole. What about binary black holes? Binary black hole is two black holes orbiting each other. So by construction, by definition, the binary black hole would be something like a binary star. Two massive objects that are orbiting each other and are not just inhabiting the same galaxy, but they have to be actually close enough to each other in order to feel the gravitational force from the partner. And again, that's an artist's impression on the left. On the right is a real image. And the reason why we think that this real image corresponds to a binary black hole, because there are jets emanating from one black hole, and then there is another series of jets emanating from the other black hole. And there have been a few more pictures. I haven't really updated the slides. I think they are maybe a bit more convincing these days, but still not something that you could easily interpret. You have to develop some sort of theoretical understanding to demonstrate that this is a binary black hole. But these are the objects that I'm going to talk about tonight. How do they form? Well, binary black holes form in galaxy collisions. And to illustrate this, let me play a movie, a galaxy merger simulation. Of course, we don't observe the collisions in real time, but we can observe them in some sort of simulations. Right? So here is one of many, many simulations that scientists run of a galaxy collision, galaxy merger, and it's set as if there were no other galaxies in the universe. Of course, they are surrounded by other things, but we can focus on just two objects that are orbiting each other, and they are not orbiting like planets, but they are orbiting like puffy bodies that can distort, deform, and eventually they collide and merge together, forming one single galaxy. And if both of these objects had black holes in their centers, then the merged galaxy will have two black holes in the center eventually. And that's how binary supermassive black holes form. And galaxies don't just merge once in their lifetime. Typically, a galaxy would have consumed a number of smaller satellites, friends or foes, in its lifetime. The nucleus is currently about to consume its largest neighbor, the Large Magellan Cloud. And in a few years, well, few giga years time, few billion years time, it will merge with the Andromeda Galaxy. Future astronomers will be able to enjoy this sound, perhaps. And galaxies typically merge several times, and if each merger creates a binary supermassive black hole in the center, then there must be something happening there if you have more than one. So here is an example how we illustrate it as a kind of a family tree, if you wish, or a species tree, or maybe just some sort of a river branching. Progenitor galaxies come and merge, and if both of them had this black dot indicating a black hole, then there will be a binary black hole sitting in the center of the merged galaxy. And as you see, at the next time, we only have one. So something must have happened to the binary black hole. And that will be the thing that I'm going to talk about. What happens to the binary black hole once it forms? So here is the outline, how the life cycle of a binary supermassive black hole looks like. It was laid out more than 40 years ago by Martin Rees in Cambridge. And I was giving this talk first time in Cambridge. I was pointing out that this guy, Martin Rees, the Lord Observant Astronomer Royal, was sitting actually in the same corridor next door to me almost. Sometimes I've seen him and talked to him about the adventures of binary supermassive black holes following his seminal work back then. So, how does it look like? Any kind of binary object, be it a star or a black hole, the main defining feature, the property of it, is the size of the orbit. So we can plot the size of the orbit on the vertical axis here, and the horizontal axis is just time. So we start from here, and the starting point is the merger of two galaxies which created this binary supermassive black hole, or rather put the two black holes in the center of the combined galaxy. And as you can see, this graph, the time goes down and down, so the distance between the black holes shrinks. And eventually, after some long and tumultuous story, these two black holes will merge, and then it will be just a single black hole, and then the galaxy is ready for the next mirror, if you wish. Of course, the next mirror might come in between, but just to make the story nice and shiny, you can say that it's always happened this way. So, but this life path is not quite uniform. It's punctuated by a series of events. And the first one, I could break it down into 4 stages. The first one is relatively slow decrease in the size of the orbit. Then there is a very rapid decrease, then again a very, very slow one, and then again a very rapid one. So these all 4 stages, they are governed by different physical processes, and that's, I'm going to go through them one at a time. And so let's start with the first one. The first stage after the galaxy merger is governed by what we call the dynamical friction. And that was the term introduced by one of the most eminent astronomers of the 20th century, Chandrasekhar. And the idea is that if two black holes, they are not living in the empty universe, they are surrounded by stars. And the stars that move around the gravitating mass, they get deflected. But they don't get deflected in exactly the same way, depending on their direction of where they come from. So let me illustrate it by the following picture. Actually, I have to first play a movie and then show the picture. So here is the movie, right? So let me just hold it a little bit. Imagine that this would be my black hole moving through a sea of stars, a uniform sea of stars. And it's not sitting still, it's moving. So if you are sitting on this black hole, you will see that stars kind of move as a headwind for you. They move from this direction preferentially, and as they do so, they will be deflected by the gravity of the black hole. So the stars that are coming from that side, they will kind of accumulate behind the black hole, and creating a sort of overdensity. The upper panel shows the same thing but kind of zoomed out, and you could convince yourself that you see a bit of overdensity behind this moving object as time goes on. So this deflection of stars is what creates this wake, dynamical friction-induced wake, and because there is a concentration of mass here, you could say that this mass is now attracting or slowing down the black hole, because the overdensity of stars here pulls the black hole back. it creates sort of a friction force. It's similar in the sense to what happens with the ordinary friction. When you're moving through a medium, you are slowed down because of friction. That's why it is called friction. But here, this friction is created because of just deflection of stars without real physical interaction. We're just accumulating stars behind this moving object. And that means that when the two black holes just move around each other, each of them will be suffering dynamic friction from the stars that surround it, and therefore they will lose orbital energy. So I could picture it as giving an analogy. If you are a celebrity on a ballroom, you're trying to move towards, to get to the bar and get your next drink, but you cannot really move easily through this crowd because there are people surrounding you, they want to get autographs or something like this, or take a picture with you, so you're suffering friction as you move through this dense medium. So this is the idea of a very dense, crowded ballroom, dynamic friction. And that's what is responsible for the first stage of evolution. So these two black holes, when they're both moving separately from each other, they don't yet know that there are two celebrities in this ballroom. Both of them are moving independently, and both of them are surrounded by their crowd of people that wanted to interact with them. And because of that, they're kind of finding their way towards the center of this ballroom. That's where the gravitational potential is the deepest, so once they lose energy, they sink deeper and deeper in the gravitational well of the galaxy, and that's where eventually they find each other. So this first stage is what leads to the formation of the binary supermassive black hole in the first place. And then the next stage is now governed not by interaction with this crowd of stars, but with interactions between individual stars. And it is also a gravitational interaction, but it's more helpful to think about it in different terms. And the most useful analogy here is the gravitational slingshot. That's the effect that is actually used in the solar system for interplanetary transport. So let me play another movie about gravitational slingshot, or rather, gravitational slingshot indeed. If you want to travel, if you want to launch a Voyager probe, you could just build a huge rocket and fire it immediately from Earth, but that would be very expensive, and that's not what people do. And most of the interplanetary missions make use of gravity assist maneuvers, mostly mediated by Jupiter, but also maybe some other planets. Yes. So if you start your interstellar probe, this is the Earth moving on a circular orbit, this is Jupiter's orbit, which is 5 times more larger, and this is my satellite. As it moves towards Jupiter, of course it slows down, and once it approaches, if you get timing right, it approaches the Jupiter just in the right time to meet it, in the apocenter of its orbit. And now, you could think about it, the Jupiter is now moving faster than your satellite. So if you are sitting on the Jupiter, you will see that the satellite, because it's moving slower, you kind of see it as going towards you. So I now zoom in onto what happens near Jupiter. My interplanetary probe will move this way, and of course as it approaches Jupiter, it will be orbiting around it and deflected backward, or nearly backward. But now, its velocity is higher than the velocity of Jupiter. So it got extra energy from Jupiter, and that's what we call the gravity assist. Now this satellite is happy to leave the solar system, and Jupiter is just going on its way, because, of course, it's not dented at all by the energy extracted by the satellite. That's how we help our own purposes of interstellar travel. Jupiter is left unscathed. But if the same thing happens with stars in the black hole is, as I said, maybe a million times larger than the star. So each single interaction of this kind will not affect the black hole, but many interactions will eventually accumulate. So what happens with the black hole is more like, you could imagine it as the following idea. Here is my binary black hole. Now two black holes are orbiting each other, and a third star comes in. And as it goes, at first nothing happens. It's just one illustration. Of course, the interactions might have very different shapes, but that's a typical illustration of what happens. If the star comes in the vicinity of at least one of the black holes, it gets into a rather complicated interaction. It might be scattered many, many times, forming very intricate patterns. I deliberately chose quite a non-trivial one here, but it's not entirely unusual, let's say. And it will just keep bouncing off and on until eventually it gets ejected with high velocity, higher than the initial velocity. So again, the concept of conservation of energy means that if the star gets higher velocity, higher energy, then this energy must be extracted from these two black holes. So it's again sort of interaction between black holes and diffuse stars, but now focused on ejecting the stars out at the expense of shrinking the orbit of the black hole, because when you extract energy, the orbit shrinks. It becomes more gravitationally bounded and black holes move faster. It's a bit non-trivial that you extract energy and the thing goes faster because the gravitational energy is negative, so when you shrink the orbit it becomes even more negative. And this is the effect that three-body encounter is like, like two football players are fighting for a ball, the ball eventually gets ejected and players get hugging each other on the ground. So this process, when it starts, it leads to very, very rapid shrinking. And this is the second stage of my picture here, because at the initial time, when the two black holes found each other, they have a sea of stars available to them to eject. And as time goes on, the stars that could have been ejected eventually get ejected. So if I now play another movie where I have a bunch of stars around this black hole, and now I speed it up by a factor of 1,000 or a bit more, so you don't see individual trajectories, but you just see that stars get ejected and the size of the black hole orbit shrinks with time. And as it does so, there will be less and less stars around it, because everyone who was able to be ejected was eventually ejected. So if you think of this process as kind of feeding the binary black hole with new fodder, you stop feeding it at some point, and what happens when you stop feeding an object? You start to starve. So that's why this rapid initial shrinking now transitions to very much slower. There are still occasional stars that just accidentally get into the vicinity of the black hole binary, only to be scattered away very quickly. And this second stage might actually is the longest one. At first people thought that it might be even kind of showstopper, in the sense that there will be almost no stars and the black holes will sit there almost forever. And that was named the final parser problem. And I was actually contributing some years ago to finding the solutions to this problem, in the sense of finding the ways to feed the stars more often to the vicinity of the black hole, so that actually doesn't get entirely starved, but it continues to evolve. But still it takes quite a lot of time. In physical units that would easily last several billions of years. So time comparable to the lifetime of the whole universe. However, if this black hole is able to, this black hole binary is able to overcome this barrier of having very few stars interacting with each other, eventually it gets to this final stage of its evolution, and this final stage is now driven not by the interactions between stars and the black hole, but more like by the emission of gravitational waves. Because, at the risk of scaring people off, I'm showing one formula here. See that people are not running from the audience, fine. One formula that just illustrates the point that the emission of gravitational waves is going very much faster when you get closer to the when the two black holes get closer. So if you get twice closer, your energy loss increases 8-fold. So that's why this last stage of its evolution becomes very easily accelerating, and then eventually the size of the orbit drops to 0. Here is another illustration of the orbit that at first looks very much like they're just orbiting each other in a circular orbit, but eventually it becomes a whirlpool pattern, and the two black holes find each other and finally merge with a loud emission of gravitational waves. And this final stage is perhaps most interesting, because in part that's what we are able to find about its the theoretical predictions exist for many decades, but it's only recently that we were able to confirm this observation, this last stage of merger between two black holes, which leads to the emission of gravitational waves. So this spiral pattern, eventually the gravitational waves are getting louder and kind of higher in pitch. I don't have a sound to play here, but you could imagine that if you were to hear it, it would look like whoop, and then this final thing is when the two black holes merge, and after a bit of ring down, we now have a single black hole. And this is kind of the final point, the arrival to the destination, if you will. And I said that it's very interesting because, in fact, these are the events that we were able to observe recently, in the less than 10 years ago. The first detection of radiation waves was in 2015, it was announced in early 2016. And this is made possible by these very sophisticated instruments on the left, the two parts of the LIGO, Gravitational Wave Observatory, both in the US. This one is the counterpart in Italy, Virgo, and this one is the CAGRA, which is still under construction, but I think they started to kind of engineering runs, or they're very close to be starting there. So what happens is that these observatories, they don't look like telescopes at all. Right? What happens here is that there are laser beams going between two mirrors, and as the gravitational wave passes through the Earth, this distance between mirrors slightly shifts, and that's what they're able to observe by very delicate interferometry. And that's another thing that was awarded the Nobel Prize another few years ago, shortly after it was discovered, because it was essentially opening a new window on the universe. Almost everything that we knew so far was based on the electromagnetic radiation, ranging from radio through optical, infrared, X-rays, and gamma rays. These are all photons, electromagnetic radiation. But this is a completely different physical image. I should say that these detections were not about supermassive black holes, they were rather about stellar mass black holes. Here's the image that these are the 4 instruments that are currently operational. There will be a few more under construction. But they are still working in the part of the spectrum, the energy frequency range, that is suitable for detecting stellar mass black holes. And that's what they've done. For supermassive black holes, because they are so much more massive, they are moving around slower, and the frequency that they emit is also much lower, so you need larger instruments to detect them. And these terrestrial observatories, they sit in this part of spectrum with high energy, high frequency, and they correspond to stellar mass black holes. If you move a few decades to lower frequencies, this is the domain of gravitational waves emitted by supermassive black holes, and they could be observed using space-based observatories, where you're not limited to 4 kilometers arm length of this interferometer, but the idea is to build the interferometer out of 3 individual flying satellites at a distance of 1 million kilometers from each other. So it will be flying in the triangular formation on the same orbit, or nearly the same orbit as the Earth, but it will be slowly trailing away from Earth. And as the gravitational wave passes through this triangle, the distance between the satellites will change again. By the same principle, it will be possible to detect gravitational waves, but now in much lower frequency range, corresponding to these binary supermassive black holes. So this LISA mission is scheduled to be launched in about 15 years from now. And in fact, the guy in my office is working on one of many people who are working on this. So I know from first hand that it's not a trivial thing to build optical instruments that would be able to operate open space and also rather extreme conditions and very high precision, but they're on the track to detecting them. And that would give us the window on the supermassive black holes that was so far not really accessible. We think that they should exist, we think that they should form, they should evolve like I just described, but we don't have observational proof yet that they merge. So that hopefully will become this kind of proof. And that's almost the end of the story, except that when they merge, there is still a final twist to the story. And that happens if the 2 black holes are not the same size, which almost always will be the case. One of them will be larger, the other is smaller. And what happens is that they, in their final run towards the coalescence, they will emit gravitational waves, but they will not emit them uniformly in all directions. So that's what anisotropy means, is that they are not emitting radiation in the same directions in the same way. And let's say the larger black hole emits slightly larger, although it's not as trivial, but you could imagine that the larger black holes emits larger share of the gravitational waves. So more energy comes in this direction than in this direction. And that means that the resulting black hole gets a recoil, much like you fire something from the nozzle, and then the firearm gets recoiled. So the remaining black hole might receive the recoil velocity, which is actually quite significant. It could be from a few hundred kilometers per second to maybe a few thousand kilometers per second. And that means that the black hole actually could even leave the galaxy, or at least be displaced from the galaxy center and flying somewhere kind of in the countryside, not in the something. And that would be the final stroke of detail in the story. So, to recap this life cycle of black holes, we start from a very, very crowded environment. We suffer dynamical friction because they kind of elbow each other to get through the crowd of stars to get to the center of the galaxy where they can form a pair. And then they start interacting with the stars individually, at first very, very rapidly. So this kind of three-body scattering, which then gets slowed down considerably, and you have a lean years, which may last many billions of years, until eventually the gravitational waves take it over and lead to the final coalescence and maybe even ejecting the black hole binary, the remaining black hole from the galaxy. So that concludes my story today.
Well, thank you very much, Eugene. That was fascinating stuff, and really, I think that gives us a really good idea of how black holes form and or how they react to the life of the galaxy. And we'll see. Is there any questions? I can't see. Ken, yes.
Yeah, thank you, Eugene. That clarifies things in my mind a great deal. I remember back in 2016 we had a talk from, I forget who it was actually, I should know the name. Martin Henry, who was dealing with black holes. That was gravity waves.
Yes, yes.
So he came to give a talk. And I was just fascinated because my idea of a black hole up to that time, up to the time you've been speaking tonight, was really the fact that there were two massive stars, huge stars, which developed as black holes when they come together. So you got binary black holes formed by two massive stars, binary massive stars.
Yes.
That's my ideal black hole.
That is it. That is completely valid. That would be the case for the stellar mass black holes.
But there's so many more.
There are more.
Current.
Yes,
Which
exactly.
I see from you. Because what caught me was when I said to Martin, the question was, wow, so you can't get very many, I can't get many binary stars which are so big to form binary black holes. So how often would you see these things? And he said to me, I don't know what you agree with, if you agree with this, he said, I was shocked, utterly shocked. I said, how often might you see these if you had... We said, perhaps once every, he said, 15 minutes. I said, what? I could not believe it.
Yeah, it depends on the sensitivity, but I think it's maybe not too far from truth.
I was thinking it would be years and years before you see one matching binary black hole, and he's talking about minutes or hours even.
Yes, okay. Yeah, I can elaborate on that. So, regarding these stellar mass black holes, this whole LIGO thing was conceived many decades ago. I was recently watching these little lectures by folks who got it by Barry Barish. That just slipped out of memory. Anyway, so what they were talking about, this was the project that was running for 2 decades without even having a chance to observe anything. They gradually increased the sensitivity. They first built a prototype. They increased it many times, several times, and every time they were hoping secretly that they will observe something, but given most theoretical estimates, they would be very unlikely to observe anything. And only when they increase the sensitivity to the point where you actually start to observe something from a relatively distant universe, then they hit gold almost immediately. That was kind of a stroke of luck, but it was not completely unimaginable in a sense. Because what happens is that when you increase the sensitivity by a factor of 2, the radius up to which you can observe objects also increases by a factor of 2, and you get 8 times larger volume. So the event rates go almost a decade in magnitude. And essentially that's what happened when they got it to the originally desired level, they were able to observe things almost every month. And now they are doing it on maybe not daily basis, but perhaps several things, maybe actually daily basis.
Wow.
You can get an app on your phone to get alerts about the gravitational wave events, and maybe just for fun, or people actually use it for follow-up observations, which are mostly done robotically because you don't want to check your phone every time and then rush to your telescope and point it somewhere. Of course, telescopes are typically much larger than you would point yourself. But these things are becoming a routine thing. And that's, I think, what will happen with the bigger space-based telescope with the supermassive black holes. At first, it might be able to detect maybe one or two, but given the prediction for this sensitivity, so this curves here correspond to the noise level, essentially the sensitivity, and the deeper the curves go, the better is the signal-to-noise ratio, the more distant objects you will be able to observe. With the LIGO, this was the original LIGO. It was barely scratching this kind of surface where you would hope to see any events. And now this is more or less the design sensitivity, and now you have quite a big margin of sensitivity, so you can observe them frequently. With LISA, you'll get quite a large margin already from the very beginning. So we'll be able to see these things almost to the edge of the universe.
Right, Scully?
As well as gravitational waves, when black holes merge, do you get a lot of electromagnetic radiation coming out as well?
That depends on whether these black holes live alone or they're surrounded by something like these accretion disks. So in this artist's impression, which is based on some physical arguments, if both black holes have gas orbiting them, you could imagine that once they merge, this gas gets very, very strongly disrupted, so there will be some sort of flare, which people hope to be able to observe. And I guess that's the answer. Not all black holes have gas around them. In some cases, like here I'm showing the examples of black holes which are bright, in the sense they emit visible light, they are observed as quasars, they emit radio waves from these jets, they emit X-ray radiation. That all comes from different phases of gas around the black hole. If there is very little gas, the black hole will be quiet. It will look more like the black hole in our Milky Way, which is, by the way, a very weak emitter of radio waves at the level of about 1 solar luminosity, even though the mass of this thing is 4 million times the Sun. So it is a very weak emitter. We see it not because it emits, but because it sits there and creates the gravitational potential. Most of the black holes look like this. They are sitting quiet. You can infer their presence from the motion of stars, but we don't see them directly. So most of these mergers perhaps will be quiet, but some of them will be accompanied by a bang.
There's still the expectation that supermassive black holes are still found only at the centre of galaxies, and the way that you get more than one is from these galaxy mergers?
Oh yes, that's a good question. So what happens if your next merger comes when this previous one wasn't really complete, right? You'll get more than 2 black holes sitting in central regions of a galaxy, and the previous one has not really had time to merge. So then you will have similar triple interaction between 3 black holes now. One of them will get ejected, and the other 2 will shrink considerably because now they're not ejecting just meager stars, but they're ejecting a chunky supermassive black hole away. So they suddenly change orbit by a lot.
Is it possible for a supermassive black hole to not be in the centre? Could it be?
Yes, initially it will be not in the center. So when the 2 galaxies merge, the black holes will be somewhere.
Yeah.
They might even be ejected during the merger itself, depending on how it proceeds. It's not impossible that the black hole just leaves the galaxy and flies away. But generally, if it stays in the galaxy, then eventually, because of dynamical friction, it will find the way to the center. Over time, because that's the bottom of the potential well. So whenever you lose energy, you sink deeper and deeper. It's much like you can launch a satellite and eventually it will fall to the Earth because of the friction against the atmosphere.
Okay.
I'm trying to get my head around the recoil.
Yeah.
If the 2 black holes are similar size, there's no recoil.
Yeah, if they are exactly the same mass, there will be no recoil. That's right, because of symmetry.
That implies then that the bigger the gap, or the difference between them, the bigger the recoil.
Yes and no. So it goes not monotonically. At first, when the difference in mass grows, the recoil velocity will be larger. But if it is very large mass ratio, like 1,000 to 1, then essentially this big black hole sits still, so it doesn't emit much of radiation. So the recoil again becomes smaller. So there is a sweet spot which happens around maybe 1 to 2, 1 to 3 mass ratio, which is probably a typical mass ratio. If you think about galaxies merging, perhaps there will be a difference of order of few. It also depends on how eccentric was the orbit. I haven't talked about it, but this interaction between stars and black holes created orbits that are gradually becoming more eccentric, and in principle this recoil velocity might be larger if the orbit is eccentric. Also depends on other factors like the spin of both black holes. So by observing some information we could be inferred about the recoil. We cannot measure the recoil directly because once the black hole has merged, it flies away, there is no gravitational radiation anymore, and we are not able to observe how fast it moves. But from the shape of the gravitational wave emitted, especially during the last stage of merger, these things, details of these oscillations matter. And that's how people already measure the properties of these binary stellar mass black holes merging from detailed modeling of this wave pattern of the gravitational waves, inferring their properties.
Following on from that, you said gravitational waves are different depending on the two, when the merger occurs. Would we be able to tell from the signature whether the larger black hole was facing us, or would we just not know?
Good question. I think what you can learn about the orientation of the orbital plane. Largest emission comes. Here is I don't quite remember what is the directional pattern of this emission. It's not uniform, right? There are some directions in which very little is emitted, but I guess you could probably learn about this, but it's not particularly interesting because if you're off by half a period, it will change the size. So it doesn't really tell you much except for like conditions that don't really matter. What matters is, what is interesting is the mass ratio between these two objects, perhaps their spins, but not maybe the orientation of the orbit because it changes so rapidly that there is no practical information.
That's great. Scully again.
The detection of the supermassive black hole gravitational waves, do you say that you need a bigger detector? Because that comes intuitive to me because I would have thought supermassive black holes would have more energy.
Yes, that's a good point, yes. So, if I go back to this picture, there are two axes on this plot. The horizontal axis is the energy, vertical axis is the amplitude of the wave. So you're right, supermassive black holes, they have higher amplitude in the emission, but it shifts towards lower frequency band. Because essentially this is the speed of light divided by the size of the orbit, and at the moment of merger, the size of the orbit is of the order of the size of the black hole. And the black hole that is solar mass, there are no solar mass black holes, there are maybe 10 solar mass black holes. Let's say, if a sun were a black hole, its gravitational radius would be 3 kilometers. Typical stellar mass black holes would have radii of several thousand kilometers. Supermassive black hole has a radius of, let's say, orbit of Earth or even Pluto if you're a chunk one. But still, in order to communicate with Voyager probes, we need the time delay is, I think, days, hours or even days. Yeah? That's the time that it takes for the light to get there. And that's roughly the frequency of the emission of the gravitational waves that come out of these black holes. So it would be in the range of millihertz, even microhertz perhaps, and that's why we need much larger instrument to measure them reliably.
Do gravitational waves suffer the equivalent of redshift?
Yes. Yes. So what happens with gravitational waves? Yes, they do have redshift, and most of the objects that we observed so far are coming from relatively nearby universe. I think the most distant one was at a redshift of still less than 1, and therefore it is there, but it's kind of absorbed in the, well, what redshift makes shifts the signal towards lower frequency. So same thing could be either interpreted as a redshift or the increase of the size of the black, or the mass of the black hole, because the frequency is inversely proportional to the mass. The higher mass, the lower frequency. But you also get the amplitude. So if you measure something that has a large enough amplitude and low frequency, then it must be intrinsically a very loud object in the first place. And if the frequency is low, then you can measure redshift. So what I'm trying to say is that people measure both the redshift, or rather they measure the distance from the amplitude, and then from the distance they will be able to infer the redshift. It's kind of a circuitous way of doing it. But with the supermassive black holes, with the LISA, we will be able to see almost, well, I said to the edge of the universe, maybe to redshifts of 5 maybe or so, so pretty far. So those eventually could be even used to put yet another handle on the expansion of the universe. By measuring the redshift from the gravitational waves, if they have an optical counterpart, you might be able to measure the redshift from the optical transients, and measuring the distance and the redshift tells us about the expansion of the universe. That's the subject of yet another Nobel Prize about the supernova and the accelerated expansion of the universe and so on. So there is plenty of physics in it.
Yeah, talking very nicely about redshift, quasars, that activity presumably is generated by supermassive black holes in central galaxies. But I believe that looking at the quasar population was actually a peak in quasar activity.
Yes.
It's a rate of about 2 or so.
Yes, yes.
So does that reflect a particular stage in the evolution of supermassive black holes and mergers? Because presumably it must have started quite early on in the history of the universe, when the density at the centre of galaxies was enough that stars formed black holes that then merged. So the stage of creation of the must vary over the lifetime of the universe.
Yes, it's almost that. I think what matters is not the density of stars, which I don't think it grows that much, or even doesn't perhaps grow at all since the redshifts of 10 up to now. What matters is the density of the objects themselves, galaxies, because the universe is expanding. The galaxies were much closer to each other back then, so they were merging more often. And that's what each merger fuels gas into the remnant of the galaxy. So eventually this gas finds its way towards the center where the black hole sits and forms the accretion disk. Accretion disk generates the emission that we observe as quasars. So indeed the epoch of quasars was quite a while ago, at redshifts between, let's say, 5 and 2. That was the peak of the rate of mergers of galaxies, the peak of activity of quasars, and we are now kind of on the decline of this curve. It will still last for many, many billions of years, but we are on the declining part of it. So I would say that it's not that the black holes were larger or smaller or anything else, but it was just the rate of events were higher.
Oh, nice. Any other questions now? Oh, yes.
What are you going to do with that yellow bit on the picture?
Ah, okay. Well, right, okay.
Was that galactic mass black holes, is it?
No, these are, so these are stellar mass black holes. These are supermassive black holes which could have a mass comparable to a smallish galaxy, but typically they're a small fraction of a galaxy's mass. In our galaxy, it's an extremely small fraction. In M87, the other galaxy that I mentioned, it was about less than 1% of the galaxy mass still, but it was some fraction. These guys would not be able, there are no black holes that we know of that would be emitting in this range. Instead, this region here is reserved for primordial gravitational waves coming from the epoch of inflation, the epoch of Big Bang. And these instruments here, which are shown the sensitivity curves, are yet another way of detecting gravitational waves, but not through the interferometry, but rather through the observation of pulsars. These are pulsar timing arrays. Pulsars are very, very precise clock, emitting signals every few milliseconds or maybe sometimes seconds. I think what they use is the number of pulsars, let's say a few dozen pulsars. So radio telescopes on Earth, they are monitoring these pulsars continuously over many years, and they see slight wobbles in the time of arrival of pulses. And this now, what we are measuring is that there is a gravitational wave coming between us and the pulsar. So the whole Earth is kind of moving with this gravitational wave, and by looking at different parts of the sky, different pulsars, measuring this time of arrival from different directions, we are able to find that there are gravitational waves. Unfortunately, this is not a very precise instrument. Whereas for these kind of events, we're able to point out where it happens. For the pulsar timing arrays, we can only measure the overall level of activity. Let's say the rough seas, right? We have several degrees of roughness, from very calm to very rough, but you cannot see by just one number where the waves come from. There's just overall level of activity. And in fact, earlier this year, so this slide is not really updated since the previous talk. Earlier this year, there were 3 papers from 3 different collaborations that declared detection of this stochastic gravitational wave background from the inflation using pulsar timing arrays. So that's ongoing science.
Interesting. Right, well, I think this has been a fascinating evening, Eugene, and we've really learned a lot about black holes, particularly mergers of black holes and how they generate gravitational waves and things. And hopefully, once LISA gets launched, you'll get lots more data.
I hope so, yes.
Yes. It's a shame it's still a few years away, but...
Well, it's a technically quite challenging object.
It is, yeah.
We need many years of preparation,
Yeah.
but I think we are well on the track.
Yes.
There are no fundamental challenges, there's just time.
Just engineering.
Challenges, yes.
Okay, so I think if we thank Eugene again for a fascinating presentation. And we'll have a cup of tea, but before tea, a couple of things. Next meeting in 2 weeks' time is Derek MacLeod from University of Edinburgh, or ROE, talking about James Webb and some new results, which should be fascinating. And also, I think you got an email about the Euclid symposium that's going to be held at the beginning of December, 7th of December. We've still got one place going. If anybody is interested, please email me and let me know. Otherwise, we'll go with 4, but we've been allocated 5 spaces. Okay, tea time. Thank you.